Okay, I propose to resume. So welcome to this third session of Eurosis. So we are going to have 4 presentations related to network performance and monitoring, including the best student paper award that will be presented as part of this session. The first presentation will be given by Iran, who is a fourth-year PhD student from Tsinghua University in China, and he's going to talk about DumpNet, a smart data center network fabric for dumb switches.
Okay, thank you. Good afternoon. I'm Iran from Tsinghua University. I'm here to present my work, DumpNet, a smart data center network fabric with dumb switches. I'd like to thank all my co-authors for their hard work and all the anonymous reviewers and Shepherd for their feedback. There is a fundamental question about the function division between network and software. The network is responsible for packet routing, network failure handling, and name service. But recent works put something like dynamic routing and co-flow optical network that all needs the help of application. So there is a problem that what should be put into the application, and the other problem is how to integrate application and the network. So let's see a data center network using internet technologies. In this kind of network, the host is very simple, but the switch, besides the packet switching logic, it should contain a lot of states and some complicated logics, and also a CPU. The problem here is the internet protocols are too complicated for data center network. And the other problem is the applications are hard to take advantage of network. Supercomputer network adopts source routing. So here the switch is very simple. It only contains a packet switching logic. And in the host, there is a fixed routing path that put into the host. And the problem is still obvious. Here, the host only supports fixed topology, and due to it use fixed routing paths, it has limited failure tolerance functions, so making it unsuitable for today's data center network. Software-defined network is an important step forward to simplify network management. It uses a centralized controller, and all the logics are put in the controller. So the switch is a little bit simpler. That is, it has the switching logic and also some states. But the state in the switch limits the port number of switch, and also it is hard to manage. And since controller puts states distributively among all the switches in the network, the state consistency problem exists. Facing those problems, we devised DumpNet. In DumpNet, we move logics and states into hosts. And in the switch, besides switching logic, there is a very, very simple fixed logic for performance issue. So the challenges including topology discovery and topology change. Let's see DumpNet. Basically, DumpNet is a tag-based routing. Use tag-based routing. When a host wants to send a packet, it will firstly query its controller for destination. And then host agent adds tags according to query result. Thirdly, while the packet is transferred in the network, the tags are popped at each hop. Let's see an example. For example, host A is sending a packet to host B. So it may add tags that is 1, 2, 3. And in the switch 1, the switch will pop the first tag that is 1, and then forward this packet through the port 1, and it reaches switch 4. And in the same way, the first tag is popped, and the remaining packet are forward to the next switch, that is switch 2. And at last, host B will receive the packet payload. So with that tag-based mechanism, we have the solution of our topology discovery. We use a host-based probe. It basically uses breadth-first search. So when it starts, the controller will send probe packet with tags 1, 2, 3, and so on. And it will receive the packet 3 comes back. So it knows it connects to the port 3 of switch 1. Okay, and put switch 1 into the queue. And then it sends more packets, that is with tags 113, 123, and so on. With 113 and 213 returns, it knows the port 1 of switch 1 connects to another switch's port 1, and the port 2 of switch 1 connects to a switch's port 1. So that is switch 4 and 5. After adding switch 4 and 5 into the queue, it will send more packets, and use the return packet to find switch 2 and 3, and the same way. Since there are no new switches found, it will know that the breadth-first search terminates, and the topology discovery terminates. For next challenge, we send an update notification to deal with topology change. It has 2 steps. The first step is to use a limited range hardware broadcast by switches. It is very simple, so the switch do not need any complicated logic. And in the second step, it uses a notification flood by hosts. Let's see an example. Suppose the port 2 of switch 1 is down. Then the switch 1 found this problem and sent a limited range notification to switch 4, switch 5, and host A. And only host A can process this message, so it will flash the notification to the other hosts. Now, every host in the network knows that the link between 1 and 5 disappears. But they still have a problem. That is, maybe some hosts in the network are using this link to transfer packets. So now the destination becomes unreachable. To deal with this problem, we further send a patch that is generated by the controller. That's quite simple. Maybe the controller will generate a patch that is use 1425 to replace the 15 and send this patch to all the hosts. So next time a host wants to send a packet through the link 15, it will use the 1425 instead. And for the performance issue, we further add a cache in the host agent. When a host queries controller for the topology, the controller actually returns a subgraph with multiple passes instead of a single shortest path. And the host agent will cache all the results and merge them into a subgraph that is called topocache. And since the topocache, the subgraph itself cannot be used to adding tags, so we generate k-shortest passes and put them into a path table. So next time, if the host agent wants to send some packet, it can firstly search in the path table, and if something matches, it can use the cache the tags to speed up in tag insertion. Now we have reached what a traditional network can do. So let's see what's the benefit of DAMnet. Let's use Flowlet as an example. Previously, if you want to support flowlet in a router, the router needs to remember available paths and need to track flow states and also some extra logics. All of those things makes the router very complicated, and maybe you need to upgrade your router to a new one. But in the DOMnet, it is very simple. You only need to add a time step to the paths in the path table. And each time you're sending a packet, you can use previous path if it is recently used. Otherwise, you can randomly choose from the k-shortest paths. Also, the application can use the TOEFL cache to provide DOMnet agent with a customized function. The function is used to adding tags. And after the checker to check that the path itself is validated, the DOMnet directly sends the packet. So you can see DOMnet helps integrate network and software very easily. So let's see the implementation. The DOMnet implementation is also very simple. It only takes about 7,500 lines of code. And to adding the flowlet, we only need 100 lines of code. And the FPGA implementation is also very simple. It uses 90% less resource consumption of an OpenFlow demo with 4 ports. The evaluation setup, we use 24-core Intel CPU for the emulation. And for experiment, we use 7 Arista switches and 27 servers. We use DPDK to insert tags and use MPLS to emulate the DOMnet switch. So as we can see, the topology discovery scales well. This is emulation result. The cube, there are 2 topologies, that is cube and fat tree. And we put controller in the different position, that is in the center of cube and in the corner of the cube. And we can see that the result for 500 switches are a little bit higher. The time is a little bit higher because at this time, our 24-core core CPU is very busy. And the next evaluation. After link failure at time 0, we can see in the left-hand side, the link failure message and the topology patch message all arrives within 10 milliseconds. And in the right-hand side, compared to the traditional STP, DOMnet recovers throughput very quickly. And at last, the blue bar in the figure is DOMnet with flowlet, and the brown bar in the figure is no-op bare DPDK. So as you can see, only with 100 lines of code, DOMnet-based flowlet easily optimizes real-world application performance. In conclusion, in this work, we rethink how to divide the responsibilities between switches and host, and how to better integrate network with software. The answer is DOMnet. In DOMnet, we try to make the switch as simple as possible to one extreme. And for the future work, we want to ask, what else must we add back to the switch to make it more powerful? Thank you.
Is there any question?
Thank you. Thank you for your interesting talk. I was wondering, with the failure notification mechanism, it seemed like you only needed the quick fix patch for just one host in your example, but does it also cover the case where one of the spine links fails?
I'm sorry?
If one of the spine links in the network, one of the more central links fails, wouldn't you need to notify a lot more of your hosts?
Okay. So you're asking about the the range of the notification, right? Okay, so as I said before, that is a limited range notification. So that is not only just one hop. For illustration in this slide, I show you a one hop broadcast, but actually we use a 5 hop. 5 hop, that is enough to reach a host. Okay, so if a core switch fails, it can also reach another host, and the host will flag the notification to other hosts. Okay?
Okay.
Okay, thank you.
Hi, thank you for the nice talk. I would like to ask 2 things. Wouldn't it make sense to already have a backup path to your first one instead of asking the controller when something fails?
You're asking about the backup path?
Yeah.
Yes. Actually, in DAMnet, we have backup path. In the slides about the total cache, I said that the controller sends a subgraph to the host. And actually, the subgraph is generated by 3 parts. The first part is the shortest path. And the second path is we consider some of the switches are failed. So we make local detours. And the third one is we remove all the switches in the shortest path and add a backup path. So all of these things will send to the host. Okay. So the host can use this path.
And I'm wondering, could you relate your work to a paper by Princeton a few years back? It's called
Saucy?
Yes.
Yes. Actually, one of our authors is the first author of Saucy.
Good.
Okay, thank you.
Thank you.
I was personally wondering, actually, what is the key motivation that motivates you to? So my question was, what is the key motivation that, as part of your perspective, motivates you to put something more actually in the dump switches now that you have put everything into the host?
You are asking about my motivation?
I mean, about your perspective, your last slide, you mentioned that you would like to add something back to the dump switches.
Yeah, okay.
Why?
Okay. That is because during the research, we want to support, for example, ECN in this network. But we found that cannot be done by current DAMnet switch, because to support ECN, the switch need to at least add some bit to the packet, but now it cannot. So maybe next step is to add some functions to the switch and let it support ECN. It is better, I think.
Okay. Thank you.
Okay, thank you.
So let's thank the speaker again. So the next speaker is coming from Hong Kong University. So it's Yu Cha. She is a postdoc at Hong Kong University, and she's going to present her paper called BDS, a centralized near-optimal overlay network for inter-data center data replication.
Thanks for the introduction, but I'm not from Hong Kong University. I come from Hong Kong University of Science and Technology. Good afternoon, everyone. My name is Yu Chao, and this work, BDS, is cooperated with these co-authors, and I thank them for all their contributions and supporting. And to begin with, for large-scale online service providers such as Google, Facebook, Baidu, an important data communication pattern is inter-DC multicast of the bulk data transfer. That is to say, replicating massive amounts of data from one source DC to multiple geographically distributed locations of multiple data centers. And these services include user logs, web search, indexes, and photo sharing, blog posts, and so on and so forth. Things are not very difficult when there are not many DCs, just replicating the data from the source DC to the destination DCs. However, in the reality, these large-scale online service providers always have hundreds or even thousands of data centers. So such simple data replication scheme is obviously not efficient because the upload link of the source DC will become the bottleneck. Intuitively, the performance of the inter-DC multicast could be substantially improved by sending data in parallel. For example, in the first cycle, data center A sends different blocks to B and C respectively, and in the second cycle, B and C exchange the blocks, and A sends the residual blocks to them. Such solution avoids the bottleneck of the source DC by using two overlay paths, A to B to C, and the other one is A to C to B to C and to B, and thus improves the replication efficiency. These two paths are bottleneck disjoint overlay paths that do not share a common link. And to quantify the potential of leveraging such bottleneck disjoint overlay paths, here we present a typical example. First, the setup and topology. Suppose we need to replicate 36 gigabytes data, which is split to 6 blocks from DC A to B and C. And there are two paths. The first one is from A to C using IP layer 1 routing with 2 gigabytes per second capacity. And the other path is from A to a server B in data center B with 6 gigabytes per second capacity, and then from B to data center C with 3 gigabytes per second capacity. And the simplest strategy is to make a direct replication, and the completion time is 18 seconds. The second strategy is to make a simple chain replication. We use application overlay paths to send blocks through server B, acting as a store and forward point. And in this scheme, the completion time is 13 seconds. So there is another strategy, we call it multicast overlay, using this bottleneck disjoint overlay paths. And we selectively select blocks, we selectively send blocks using two bottleneck disjoint overlay paths. And in the first cycle, A sends 3 blocks to B and 1 block to C. And then B sends the 3 downloaded blocks to C, and A sends the residual 2 blocks to C. Such scheme completes the replication in just 9 seconds. This example gives us the key insight that the inter-DC multicast could be substantially improved by sending data in parallel while bottleneck disjoint overlay paths. So what's the bottleneck disjoint overlay path? We define it as the two paths that do not share a common link or intermediate server. In the context of inter-DC data transfers, there are two kinds of bottleneck disjoint overlay paths. The first one is the two paths that traverse different sequences of DCs, like the prior example shows. And the second one is the two paths that traverse different sequences of servers of the same sequence of DCs, just like the example that we introduced, which completes in just 9 seconds. So on the base of the bottleneck disjoint overlay path, we present BDS, which is a centralized network for inter-DC data replications. And the objective of BDS is to achieve near optimal performance by taking advantage of the bottleneck disjoint overlay path using an efficient enough control logic. For the basic formulation, BDS takes the following parameters as input, such as data blocks and scheduling cycle and link capacity. And in each scheduling cycle, BDS returns a two tuple as output. We select, the first one is whether server S is selected as the transmission destination server and how much bandwidth we could allocate to each transmissions. Of course, such formulation have multiple constraints. So, for example, the constraints on allocated bandwidth and on link capacity and transfer blocks and scheduling cycle. These constraints make the formulation incredible in practice because it is superlinear and mixed integer. So the computation overhead grows exponentially with more potential source servers and data blocks. To address this challenge, the key insight behind BDS is to decouple the aforementioned formulation into two steps of a scheduling step, which selects a subset of blocks to be transferred in each cycle, followed by a subsequent routing step, which picks the path and allocate bandwidth to transfer to the selected blocks. So take the previous scenario as an example. Select a subset of the blocks to be transferred in this cycle. This is a scheduling step. And then pick the path, allocate bandwidth, and execute the transmission is the routing step. And then here is another scheduling step, and the transmission is another routing step. Such decoupling significantly reduced the computation overhead of the centralized controller, as the scheduling step just selects a subset of blocks, and only these selected blocks are considered in the subsequent routing step. So the sorting space of the routing step is significantly reduced. As the implementation, there are three main components of BDS: agents, controller, and monitors. It starts with the agent running locally on each server and checking the local status, and then report the status to the centralized BDS controller via agent monitor. The BDS controller also receives network level statistics from network monitor, and then runs the centralized decision-making logic to work out new scheduling and routing decisions, and then sends those decisions to the agents via the agent monitor. Finally, the agent carries out the actual data transmissions according to the controller's decisions. We have implemented BDS in Golang code and deployed it in tens of Baidu's geographically distributed data centers in China. Baidu's current solution of inter-DC multicast is called Ginkgo. So we begin by evaluating BDS and Ginkgo on one service that needs to distribute 70 terabytes data from 1 source data centers to 10 destination DCs. And these figures show the details and the CDF of the completion time on each destination servers. Of course, lower is better. And from these figures, we can see that BDS consistently outperforms Ginkgo by 4 to 5 times. Complementary to the pilot deployment on real traffic, we also use trace-driven simulations to evaluate BDS on a larger scale. We simulate two other overlay multicast techniques, Bullet from Duke University and Akamai's overlay network. We see that BDS achieves 3 times shorter completion time than Bullet and Akamai in the baseline setup, and even over 4 times shorter completion time in the large-scale and small bandwidth setups, which shows that BDS has greater improvements in extreme cases. Next, we use macro benchmarkings to evaluate the scalability of BDS. The left figure shows the running time as a function of the total number of blocks. To put this figure into perspective, in Baidu's DCs, the maximum number of the simultaneously blocks is around 300,000, for which BDS can finish the calculating within 300 microseconds. And the figure in the middle shows the network delay of 5,000 requests. We can see that 90% of the network delays are below 50 microseconds, and the average value is about 25 microseconds, which is less than 1% of the decision updating cycle, and the default value is 3 seconds. And we also measure the delay of the whole process, like the figure on the right. In most cases, over 80%, and the feedback loop delay is lower than 200 microseconds. To sum up, we can claim that BDS demonstrates a short enough latency and is able to scale to even larger systems. Further, we examine the impact of different failure scenarios on the number of downloaded blocks per cycle. During the first 9 cycles, BDS works as usual, and in the 10th cycle, one agent failed, and we find a slight impact. The system then recovers in the 11th cycle. And the controller fails in the 20th cycle. BDS then falls back to a default decentralized overlay protocol, resulting in graceful performance degradation. But when the controller recovers in the 30th cycle, the performance recovers. So BDS has strong robustness under failures. And to sum up, BDS in one slide, what is BDS? It is a centralized near-optimal overlay network for inter-data center data replications. And here are 2 takeaways. The first one is that bottleneck disjoint paths could potentially improve data replication performance. And the second is the decoupling of scheduling and routing to speed up the execution of a centralized algorithm. And we believe that such insight of decoupling can be generalized to other centralized control platforms, where centralized decision-making solutions strikes for a favorable balance between costs and benefits. So that's all for my presentation, and thank you.
Thank you. Question?
Nice work, straightforward to understand. I have a simple question. In cases where you have multiple source server, then what's going to happen? That's my question. You actually use intelligent replication to leverage disjoint path, but at the runtime, it is possible that some of the links will be busy in cases where you have multiple servers to transport the data, right?
Yeah, thank you for your question. And actually, this is a key key part of the detailed algorithm of BDS. And BDS consists of two parts. The first one is selecting which data center should be selected as data source, and the second part is how much bandwidth should we allocate to the source and destination pair. And the question you mentioned is how to select the data source. We will compare all the different scenarios of different choice. We choose different data centers as data source, and we compare all the solutions that we evaluate which path, which source and destination pair could lead to the maximum allocated bandwidth, and we choose the data source that could potentially maximize the total allocated bandwidth. And this is the method of how we choose the data source. Did I answer your question?
Not really. Yeah, we can talk about such a things offline. Yeah.
Okay.
Any other question? Yeah, I also had one question. Actually, the block size that you mentioned in your big picture, that's something that you define by yourself for the time being?
You mean the block size?
Yeah.
We evaluate different size of the blocks, and we already tried 2 megabytes data megabytes as a block, and 60 to 64 megabytes data as a block size, and we finally decide to split the data into 2 megabytes per block, and for the balance of the cost and the performance.
And is that something that you could actually compute, the optimal size of the block, depending on your topology and current state of the network?
The size of the block will not affect the topology of the algorithm, but the size of the block will affect the computation overhead and the optimization performance. Yeah.
Okay. And my other question is related to the fact that you separate routing and scheduling.
Yeah.
And does it offer some venues for new scheduling, actually, policies that could be considered depending on application case studies, typically?
You mean why we decouple the two processes?
Yeah, I mean, it's interesting to decouple, but then one of the benefits is that then you can also change the scheduling policies for some specific reason.
If we do not decouple, if we couple the two processes, the computation overhead could be extremely high, and for the scale of the Baidu service, it cannot the centralized controller cannot hold that scale.
Okay. Thank you.
Thank you. Sorry.
Okay. So the next presentation is actually the Best Student Paper Award that has been awarded this morning. So it's been given by John Sonchak, who is a PhD student at the University of Pennsylvania. And the paper is entitled TurboFlow Information-Rich Flow Record Generation on Commodity Switches.
Okay, well, thank you for the introduction. I'm really glad to be here this afternoon and to have some of your time to talk about this work. So this is work that I've done with my collaborators Adam Aviv and Eric Keller and my advisor Jonathan Smith. So TurboFlow is about supporting network monitoring applications that use flow records. And so a flow record is basically just a compact summary of a sequence of packets between two endpoints in the network. So think of one direction of a TCP or UDP socket. And so a flow record contains statistics and metadata that summarizes the packets in the flow and also how they were processed by the network. And flow records are widely used in practice. They're often called NetFlow or IPFIX records. And they're valuable because they provide visibility into what's going on in your network. So typically the way we use flow records is switches and routers in the data plane will export flow records to applications. And the applications will analyze them for many different reasons. So a debugger, for example, might analyze flow records to pinpoint the root cause of performance-related issues in the network. A traffic engineering application may analyze flow records to find traffic flows that are competing for bandwidth on congested links so that it can reroute some of those flows on alternate paths, easing network congestion. Security applications analyze flow records for many different things to detect threats like botnets or denial of service attacks, and so on. So flow records are a really powerful abstraction for the monitoring applications. But the challenge that we're dealing with here is that it's actually challenging to generate the flow records from the perspective of a switch or a router in the network. And it's challenging because the forwarding rates are so high. Multiple terabit per second forwarding in switches corresponding to hundreds of millions of packets per second and tens of millions of new flows per second. And so typically what we do in commodity switches today is sampling. So the underlying data plane hardware of the switch clones a fraction of randomly selected packets up to a software process running on the switch CPU, and then that software process generates the flow records. The sampling lets the software cope with the high rates, but this sacrifices the accuracy of the records. It skews the features and it causes the flow records to completely miss short flows. Now, to overcome the limitations of sampling, prior approaches mostly focus on offloading, kind of taking the work that you need to do to generate flow records and pushing it off somewhere else, either to clusters of servers, which is expensive because you need many servers to cover the packets forwarded even by an individual switch, or to custom hardware, such as NetFlow ASICs. And custom hardware is limiting in a different way because it restricts you to flow features that are baked into the hardware. It also locks you into using non-commodity switches. And so the idea in TurboFlow is, instead of offloading, let's try optimizing. And we think that now is a good time to revisit what we can get out of the switch hardware that's already there, because switch hardware is changing so rapidly these days. The next generation of commodity switches that's kind of currently coming to market integrates programmable forwarding engines. So these are kind of line rate forwarding engines that have reconfigurable match action pipelines, things like P4 or similar match action programming models. Switches are also integrating more capable CPUs. Previously you would have a switch with a very weak embedded systems processor in it. Today, because processors, the power consumption of general purpose processors has been optimized a lot. Today in switches you have general purpose hardware that more closely resembles what you would find in a server, kind of just scaled down to fit within the power budget of the switch. And so we want to look in TurboFlow, what can we get out of this new hardware in the switch for flow record generation? And it turns out that with the right design, with a careful design that utilizes this hardware efficiently, we can scale flow record generation up to multi-terabit rate traffic workloads without having to sample or offload any of the work to custom hardware or clusters of servers. And so the hardware makes it possible, but it doesn't necessarily make it easy. If you think about either of these components, neither of them can support flow record generation by itself. The forwarding engines are more flexible, but you still can't do all of the complex logic required to generate flow records in the forwarding engine itself. The switch CPUs have more features, but they still don't have the throughput necessary to generate flow records at terabit rates on their own. And so the challenge with TurboFlow is to basically two things. First, to figure out a way to partition the work between the two processing components of the switch, and then to figure out how to actually do that work efficiently on those processors to kind of make the most of them. And so at a high level, TurboFlow takes an incremental approach to flow record generation. So the forwarding engine aggregates packets into what we call partial flow records, or micro flow records in the paper. And so the idea here is every packet is accounted for in one of the partial flow records, but the statistics for a complete flow may be spread out across multiple records. So the CPU still has to do some work aggregating those partial flow records into complete flow records, but that amount of work is much less than if it were operating on individual packets. And so in this presentation, I'm going to talk a little bit about some of the highlights of TurboFlow's architecture, focusing on how we implement the pre-aggregation efficiently in the forwarding engine and the complete flow record generation efficiently in software. Then I'll touch on some of the highlights of our evaluation and conclude pointing out some of the other interesting stuff you can find in our paper. So let's start by talking about the forwarding engine component of TurboFlow that aggregates packets into partial flow records. So a little bit of background. The data plane hardware of a switch, the forwarding engine, processes packets at line rate using a pipeline of configurable match action tables. And so each table contains rules that you kind of customize and define how they look. And a rule contains three main components. First, a match field that defines what packets the rule applies to. Second, an action that tells the switch how it should process matching packets. And third, kind of most interesting for TurboFlow, is stateful variables. Stateful variables store counters and statistics that persist across packets. So the goal here with TurboFlow is we want to use these match action tables to measure statistics about different flows that the switch is observing. Now, the simplest approach would be to use per flow rules. So when a flow starts, you install a new rule into the switch to track that flow. You count statistics for it until the flow ends, and then at that point you export the statistics to the CPU. The problem is this simple approach doesn't actually work because we don't have enough time to install a rule for each flow. Installing a rule is a complex and expensive operation. It requires kind of changing data structures and doing a lot of maintenance operations, and it's something that we need to invoke the CPU to do. So we're off by orders of magnitude if we want to install a new flow rule for every fine-grained TCP or UDP flow in a programmable switch. And so with TurboFlow, the key insight about the forwarding engine component is that we design a table that's more complex, but it completely avoids the need to add new rules at runtime. And so the key is to take more advantage of the stateful capabilities of programmable forwarding engines. So in TurboFlow, each of the rules in this table stores not just counters and statistics about the flow, but also a IP5 tuple. And so essentially a rule remembers which flow it's tracking and automatically adapts over time to track different flows as the traffic changes. So once you install a rule, essentially it never has to be replaced. So at startup, we install a bunch of these rules into a fixed size table. And then at runtime in the network, we use a hash of each packet's IP5 tuple to map it to a rule. And so if the packet belongs to the flow that the rule is tracking, the rule just updates the counters for that flow. On the other hand, if the packet doesn't belong to the currently tracked flow, the rule replaces the old entry with an entry for the new packet and sends a record of the old flow as a partial flow record up to the switch CPU. And so the CPU will still have to do work aggregating these partial flow records together, but on average, each of these partial flow records will represent multiple packets, and so that work is much less than if it was operating on individual packet records. So there are a lot of details about this in the paper, including an expected worst case bound on how frequently these evictions happen. What I want to focus on in this presentation for a few minutes next is how we optimize the software to efficiently convert the partial flow records into complete flow records. The bottleneck in the software is basically the dictionary data structure that maps the partial flow records to complete flow records. It's essentially a hash table. And so hash tables are a common bottleneck in software packet processors, in routers and switches. But the workload for TurboFlow is a little bit different because the entries change very frequently. So whenever a new fine-grained TCP or UDP flow starts or ends, we need to update the entries in the dictionary. And so this is much different than a router or a switch that has a lookup table that does not change very often. So what we did was we started with kind of a clean slate, a reasonably efficient implementation using the C++ standard library's unordered map. And then we looked for ways to optimize it, just kind of finding what the bottlenecks were. And so we basically found that with these three important optimizations, reducing the number of pointer operations, vectorizing the key comparison, so instead of using memcomp, we're using SSE instructions in the x86 CPU, and also batching and prefetching to reduce cache misses. These optimizations improved performance by a factor of about 5 and got us down to about 146 cycles spent per partial flow record. For context, that's less time than it takes the fast path of Open vSwitch to process an individual packet. So it's a pretty efficient implementation. The details of these optimizations are in the paper, but what I want to talk about next is a little bit on our implementations and evaluation of TurboFlow. So we have two implementations of TurboFlow, and the source code will be available soon. One is for a barefoot Tofino switch. This forwards packets with a 3.2 terabit per second forwarding engine that you program in P4, and the barefoot compiler compiles the P4 kind of into a configuration of the actual hardware. And second, we have an implementation for a Metronome P4 SmartNIC. This architecture more resembles kind of traditional network processors. So we evaluated these implementations with traces from 10 gigabit internet links from CADA and a simulated data center cluster trace. I'm just going to talk for a moment about some of the high-level results from the P4 switch implementation with the 10 gigabit router link traces. And so we're going to look at the throughput that the switch CPU needs to sustain in terms of partial flow records per second in order to support the equivalent of 100 10 gigabit per second links. So this is essentially a terabit of aggregate capacity with the profile of core internet router links. So first, this is the workload that it would need to support with and without aggregation by the forwarding engine. So the red line at the top is a scenario where every packet, or rather every partial flow record, represents exactly one packet. So this is basically the workload that it would be doing if the CPU was operating directly on every packet. The green line represents the work that it has to do using 5 megabytes of forwarding engine memory, about 25% of the forwarding engine's SRAM, for a stateful table to do the pre-aggregation. And so with about 25% of forwarding engine memory, we reduce the workload of the CPU by a factor of 4. So next, these lines show the throughput of the CPU component with and without our optimizations. And so as we saw before, the optimizations improve throughput by approximately a factor of 5. And the key takeaway here is that these optimizations let us comfortably, both the optimizations and the pre-aggregation in the forwarding engine, lets us kind of comfortably hit the watermark of terabit rate flow record generation using a reasonable amount of switch resources in terms of both CPU cores and memory in the lower level forwarding engine. So that's all that I'm going to talk about today. There are a lot more details in the paper, evaluations on the data center traces, pseudocode, implementation details, formulas, cost analysis, lots of diagrams, so please skim it. But if there's two things that I hope you will remember about this work, it's that flow records are a really important and useful abstraction for monitoring, and TurboFlow is a system that's carefully optimized that lets kind of existing next generation commodity switch hardware scale to generate flow records for multi-terabit traffic without sampling. Thanks.
Hi, is this on? Yeah. Joel from ETH Zurich. This is very impressive stuff. I have a question. It looks like a lot of the complexity goes into splitting the work and figuring out how to make this work in software, like the parts in software. Mm-hmm. If you could have a wish list for a few simple additions to the forwarding engine or change P4 a little bit, could you actually move this all back to hardware, or is, what's your feeling on that? Like, yeah.
Yeah, that's a great question. So I think there's two challenges. The first is the complexity of the logic that you can implement in the hardware. And I think that as the cost of logic goes down, we will see more advanced forwarding engine designs. So that will be beneficial to kind of let us use the forwarding engine memory more efficiently. A more longer term problem is that we don't really have that much memory to store this data in the forwarding engine because we're using SRAM. And so even if we had, arbitrarily complex logic that we could put into P4, we'd still be limited by the amount of memory that we had there. So we would need to take some sort of a kind of partial or incremental approach to the problem.
Dushint Narayan in Microsoft Research. I'm just wondering, in your current implementation, did you ever run into two very heavy flows which collided in your hash table, and what did that do to your performance?
So not in the workloads that we used. It's certainly a possibility, right? And I think that that would hurt performance a lot. If it was something like an adversary, I think the solution would be to investigate some sort of kind of collision mitigation mechanisms to kind of detect those scenarios and change the key or something to avoid them.
A quick follow-up similar to that. What is the failure mode if you get a huge amount of these partials? What does the CPU do if it can't keep up?
So we haven't considered that aspect of it, the failure mode. Right now it just buffers and then eventually drops them. So, yeah. But that's definitely an important aspect. And I think, like, kind of in general, looking at the security of these kind of data plane telemetry systems is like a very important direction for future research, because that kind of question applies to a lot of different things that have been proposed recently, I think.
You can use yours, but you need an adapter. Okay. So I let you plug it. To your PhD student. Anyone? So, what's that?
I'm currently a software engineer.
Okay. Yeah. Okay. So you're? Okay, so we're moving towards the end of the session. So the last paper is going to be presented by Chen-Shun Jung from University of Southern California, and the title of the paper is entitled "Wide Area Analytics for with Multiple Resources." Oops.
is there? Okay.
Here it is.
Okay. Thanks for the introduction. My name is Chen Hong. Today I'm going to talk about wide area analytics with multiple resources. This work was done when I was a PhD student back in University of Southern California. And this work was in collaboration with other authors from Microsoft Research and Harvard University. Okay, so let's talk about wide area data analytics. Due to the growing needs in computation and the increasing volume of data, nowadays major cloud companies are deploying more and more data centers across the world in order to provide a low latency response time for various applications. So depending on the characteristics of the applications, their data might be generated, stored, or processed across multiple locations. And therefore, we call the type of applications as wide area data analytics. Some common applications include analyzing user session logs or monitoring or troubleshooting for system health. And oftentimes, such applications, they require fast response time. And fast response time is critical for making real-time decisions. So the architecture of this wide area analytics involves multiple data centers across the world. And depending on the deployment constraints, each data center may have different capacity in terms of computing powers or network bandwidth. So for example, the number of computing slots at each data center across data centers may differ by up to 2 orders of magnitudes. And the bandwidth may differ by up to 18 times to 25 times. And also, depending on the type of applications, the required data volumes could differ by up to 22 times. And applications of the wide area data analytics, they are often submitted as jobs with data parallel tasks. And there's a global manager on top of those data centers that is in charge of scheduling these jobs and coordinating across multiple data centers. And in which the decisions of scheduling the jobs include assigning a task with one of the slots in one of the data centers, and also decide the order of the jobs getting executed. So in this work, the task placement and job scheduling are the 2 main focuses of this wide area data analytics. So some existing solutions. First of all, there's a centralized approach that basically aggregates all of the required data at a single site upfront. The downside of this approach is that it incurs lots of data transfer across the world, and incurs a significant delay. The second approach is in-place approach, which basically instead of moving the data for computation, it actually moves the computation for meeting the data locality. The downside of it is that it performs poor when there's a mismatch between data and resource capacity. And more recently, there's a third approach called network-centric approach, that basically distribute the tasks to minimize the network transfer delay across multiple locations. The downside of it is that it ignores the other constraints like computation capacity. So to address those limitations in the existing approach and develop our own solutions, we break down the problems into 2 major challenges. The first challenge is the heterogeneity in the resource distribution and its mismatch with resource demands. So let's use a simple example to describe the idea. So in this simple example, there are 3 sites. And for example, the site 1 has the most number of compute slots, but has the least download bandwidth. On the other hand, the site 2 has the most volume of data to process, which requires the most number of map tasks to process, but also has the least number of compute slots. Now, the common approach for map task placement is site locality approach, which basically leaves all of the map tasks to run locally in order to meet data locality, which results in 0 network transfer time. But it will incur significant computation time, especially for site 2, since it has the most volume of data to process, but has the least number of computing slots. The optimal approach in this example would be shifting some of the data from site 2 to site 1 and site 3, which brings down the computation time from 45 seconds to 23 seconds, with a minor increase in network transfer time. But overall, the optimal approach has almost cut down the overall total duration by half. So this example tells us that it is important to optimize for both network and computation time. So in our task assignment solution, we basically break down the total duration into network transfer followed by a computation time. In the network transfer time, it's equivalent to the data size divided by the bandwidth. And given n sites in the architecture, we will have n squared number of data upload and data download. And the overall network transfer time is determined by the bottleneck of all of the transfers. For the computation time, it is estimated based on the number of waves to complete all of the tasks. And the number of waves is defined as the number of tasks divided by the number of slots in each data center. And also, it is determined based on the bottleneck of across all of the sites. So basically what we did is that we formulated this task placement problem into a linear program optimization model with the goal to minimize the network transfer time plus computation time. So to give you some ideas about how this linear program looks like, here's the formulation. So in this formulation, the variable is mxy, which basically means the fraction of map task placed at site y but needs to read data from site x. So the overall goal is to minimize the sum of network transfer time and computation time, in which the network transfer time is determined by, it should be larger than all of the network transfer time, whether it is upload or downloading time. And the computation time is determined by the bottleneck of computation time across all of the sites, which is basically the average task duration times the number of waves. And we have the similar formulation for reduced task placement, but with a slight difference in that here the variable Rx is just a fraction of reduced task placed at site X, because each reduced task basically needs to read the data from all of the map task output, so we don't have to specify where it reads data from. Other than that, the formulation is similar. We are also minimizing the sum of network transfer time plus the computation time, while the network transfer time is determined by the bottleneck of all of the upload and downloading time. And the computation time is also determined by the number of waves times the number of the average execution time. Okay, so the second challenge is that there's a complex interdependency between task placement and job scheduling decisions. So let's use another example to explain this idea. In this simple example, we also have 3 sites, and in each site we have 3 computing slots. And to simplify the example here, the upload and download bandwidths are all 1 gigabyte per second for all of the sites. And each task requires 100 megabytes data input. And to complete each task, it takes 1 second. And we have two different jobs. The first job requires 0, 1, and 2 tasks across all the sites. And the second job requires 2, 4, and 6 tasks across all of the sites. So their ideal placement, which runs them exclusively, is to place basically 0, 1, and 2 for job 1, and 2, 4, and 6 for job 2. And the resulting average response time is 1.5 seconds. But in reality, they are concurrent jobs. So we have to decide their orders. If you run job A first, and then run job B, in this case, job A will get its ideal placement, but job B will have the placement for 6, 4, and 2, which results in an extended delay. It's 2.4 seconds, and the overall response time is 1.7 in average. If we have a different order, by running job B first and then run job A, job B will get its ideal placement, but not job A. For job A, we'll have to shift all of the data from site 2 and site 3 to site 1, and run all of its tasks inside one, which has a 2.3 seconds in its response time. And the overall response time in average is 2.15 seconds. So here the example tells us that in the optimal schedule, not all of the jobs would get their ideal placement. And this is due to the complex interaction between job scheduling and task placement. So in our solution, we basically decouple the decisions of job scheduling and task placement. In the job scheduling part, we schedule the faster jobs first to reduce the waiting time, which is basically the philosophy of shortest job first. And the job duration is estimated based on how each job plays their task. So remember that when we have the linear program model, by solving that optimization model, we not only get the task placement, but we also get an estimated duration for a completion time for the job. And for the task placement part, we basically solve that LP model based on the remaining network and computation resources in order to minimize the computation time. And the remaining capacity is determined by the order of jobs getting executed. Now in here, our solution basically will favor the faster jobs and assigns as much resources as it requires as possible. However, some other jobs may starve. So we further propose to have a control knob, epsilon, to balance in between response time and fairness. So here, with the epsilon, each job will be guaranteed to have at least 1 minus epsilon times this fraction of slots. And the number of the slots that each job can get is kept by the total number of slots minus the reserved slots for each job. So when epsilon approaches 0, our design becomes completely fairness-oriented, while when epsilon approaches 1, it becomes completely response time-oriented. So with this control knob, we have a nice handle to balance between fairness and response time. To summarize our design, each scheduling instance in our solution is triggered by whenever there's a new job arrives or whenever there are new slots become available. So whenever a scheduling instance starts, we first solve the linear program model for each job and gets its estimated completion time. And based on that, we select a job with the shortest completion time and assigns the resources to it according to its task placement decision. And we keep doing this until all of the available slots are allocated or when all of the jobs are getting allocated with slots. So to talk about our prototype and evaluation, we built our prototype on top of Spark. So basically we inject our own scheduling algorithm and task placement solution into the scheduler module. And we estimate the task running time based on its peer tasks. And also we batch some available slots in order to reduce the scheduling dynamics. And our scheduling solution will call out for GroupB solver to solve the LP optimizations. And in our evaluation, we have a deployment with the geo-distributed EC2 cluster. We have 2 benchmarks. The first one is TPC-DS, which has the longer stages of tasks. And the second one is big data benchmark, which has shorter stages of tasks. In addition to the real deployment, we also have trace-based simulations. The traces from a 3,000 machine production cluster. So to talk about the major results, here we have 3 different baselines. The first one is in place, which is basically the default Spark behavior that apply in place for map task placement and apply fair scheduling across the jobs. And the second is Iridium, which is the recent network-centric approach that minimizes the network transfer delay while also applying fair scheduling across jobs. And the third one is centralized, we basically aggregate all the data upfront. So here, from the left figure, we can see that our gains are up to 77% and 55% compared to in-place and Iridium approach in terms of the reduction of response time. And our gains are higher when there are more number of data centers in the architecture or when the workloads are more heavier. And the second graph on the right-hand side shows that if we replace each of our module, for example, if we replace job scheduling with fare scheduling or other solutions, what would be the performance gains? So it shows that both our job scheduling and task placement solution module are important to our gains. And this figure shows how do we balance between response time and fairness. So in this figure, it shows that we will achieve the comparable gains in response time, even when each job is guaranteed to have 60% in proportional to the number of slots. Other key results include that our gains are universal across all different job sites. And our gains are more when the intermediate to input data ratio are higher. In terms of the scheduling overhead, each scheduling decision roughly runs for 1 second, and solving each LP optimization model takes roughly 100 milliseconds. And we were able to keep the overall overhead low by focusing only on the faster jobs. Okay, this concludes my presentation, and thank you. I'm happy to take some questions.
John Wilkes, Google. A really dumb, naive question. You talked about adding network time and compute time together. What happens if they overlap?
Oh, you're saying that they might be overlapping with each other, right?
Yeah.
Yeah. So here we are doing a worst case estimation. We do that, basically the overall response time is determined by the lastly finished task. Well, we might have the longest sum of network transfer time and computation time. So basically we're just doing a worst case estimation to get an idea of how the overall response time would be.
Do you think it would be any better if you were a little smarter?
What's that? I'm sorry.
Do you think you could do better if you took account the fact of potential overlaps?
Yes.
Could you search for overlaps to try and make the thing go faster?
Yes, it's totally possible. It's part of our ongoing works actually. So here we're only utilizing the worst case analysis, but it's totally possible that they will overlap with each other. Thanks.
Hi. Hi. So there have been some work in the past that distribute workload, maybe to maximize profits or green energy usage across distributed data centers. So I think that in your case, you primarily maximize performance.
That's right.
So how would you integrate other possible targets, like maximizing profits, into your framework? How the two would combine? I mean, which one you would?
Can you give an example, like how what are the performance metrics would be?
So sometimes, like, consider you have two data centers. One of them can use green energy, so that would decrease the costs. The other one doesn't have any of those, so it costs more, but maybe it performs better than the other one. So you have to decide, between profits and performance. So how you balance the two? Would that complicate a lot the problem?
A good point. So in this short presentation, I didn't go through all the details. So in our paper, we do consider, for example, other metrics would be if we want to minimize the bandwidth cost, what would be the performance? So we are able to incorporate that, for example, the bandwidth cost as another control knob, in addition to minimizing for response time, just like how we did for balancing between fairness and response time. Yeah. So for more details, please go to our paper. We have some more solutions there. Thank you.
Any other question? I had one actually. I was wondering, in this kind of system about analytics, do you have some kind of recurrent tasks that you need to execute every day or every week? And I mean, having this knowledge, can it be used actually to improve the scheduling and the performance of the system?
Yeah, that's a good question. So here I talk about one of our implementation details is that we would estimate the task running time based on its peer task. But like you said, some of the jobs, they are recurring jobs. So if we can get some history data from the previously run jobs, then we will have an idea of how the task, like how long the task would run. So instead of using the estimated the task information, we can actually apply the history information to get a better sense of how long each task would run.
Okay.
Thanks.
No more question? So let's thank the speaker again.
Thank you.